Hey everyone, and welcome to the Chapter 17 lecture on kinetics. So kinetics are the study of the speed or rate of chemical reactions. Rate, speed, not really the same thing, but kind of the same thing for intents and purposes of this chapter. So what is rate? How do we measure the rate of a chemical reaction? Well, it's the change in the amount of substances produced divided by the change in time. So it's the, change, and we measure the amount by concentration. So it's the change in concentration, and we can measure it in it can be the change in concentration of reactants or products. Over, the change in time. So the way that we can do this, write this out in a sort of shorthand chemistry notation, change, we represent with the Greek letter delta, triangle, and concentration we put in brackets. So any number with brackets around it, square brackets, indicates a concentration, usually of molarity, over change in time. Okay, so the units for rate are going to be concentration, molarity, per second, because the SI unit for time is seconds. So that's the typical units for rate, molarity per second. So let's look at some generic reaction. We have the reactant A is being converted into the product B. So if we were to graph this reaction, where on the x-axis I have time in seconds, and on the y-axis I have concentration in molarity, moles per liter. I'm going to start with the reactants. So what happens? Well, when we start a reaction, at the beginning of this reaction, we should have just A. We have some A, and we have no product at time 0. So our starting amounts these are our starting points for each. As the reaction goes, when we start the reaction, what happens is the reactants start turning to products. So the amount of reactant drops and then levels off, and the amount of product rises and then levels off. All right, so notice that the initial slope of each of these lines is pretty steep at first, and then it kind of, the steepness declines and it even levels out and straightens out, okay? So what this means is that the rate of the reaction starts out initially faster, and then it slows down as the reaction progresses. Okay, so just to illustrate that, I have this little video clip, if it'll work. Okay, let's see. Here it is. Nope. Scooch it back a little bit. So this is just a reaction. It's a catalytic decomposition of hydrogen peroxide, but it's a real good illustration of how the reaction rate initially starts very fast and then it slows down. So in this reaction, hydrogen peroxide, it decomposes into a gas, and you can see the smoke plume come out. So initially it smokes, it produces and bubbles very quickly, and then it kind of tapers off there and putters out. We're going to see it again from a different angle. All right, you see that heavy, violent bubbling there, and then it kind of fizzles out. So initially, the rate is very fast, and then it slows down, and it eventually tapers off. Okay, so that's just an illustration, or trying to show you an actual reaction, so you can see what I mean by this graph, that the reactants fall off and the products are made. Okay, so for this reaction, what we can do is we can write out the rate expression. So rate, we defined it as the change in concentration over the change in time, right? And so for this reaction, this means thus for this reaction, the rate is equal to, it's the negative change in concentration of our reactant, because the reactant concentration goes down, and rate should always be a positive value. So if the change in concentration of A is going to be a negative number, then we need to negate that with the negative sign so that we'll have a positive value for rate. Okay, so the rate of the reactant declining is equal to the rate of the product forming. So these two rates are going to be equal to each other. Another way to think of this rate in terms of this graph is that the rate is actually it's the slope. All right, and the slope is actually changing because this is a curve, it's not a straight line. But the slope of a straight line is rise over run, right? Rise over run. And the rise here is concentration, and the run is time. And what is rate but change in concentration over change in time? So if we were to pick a point on this line, actually, I take it back. If we're trying to find the average rate over a period of time, and we pick 2 points on a line, and we find the straight line between those 2 points, that's the average rate. So it's not the exact rate, because the rate is, of course, changing throughout the course of the reaction. So this is how we use the rate expression. By the way, this is called a rate expression. And we use it to calculate the average rate. And what it is it's the slope of a straight line between 2 points on that graph. So in that simple reaction, what we didn't account for was coefficients. So 1A became 1B. But let's look at a slightly more complex general equation where it does have coefficients. So these lowercase a, b, c, and d, lowercase letters represent coefficients. So, a number in front of the chemical formula. So for this reaction, the rate expression would be as follows. So it's going to be the negative 1 over A, that coefficient, times the change in concentration of A over the change in time, which will also equal negative 1 over B times the change in concentration of B over change in time, which will equal positive 1 over C times the change in concentration of C over the change in time, and positive 1 over D times the change in concentration of D over the change in time. Okay, so the amount of time, so over some period of time, let's say, 10 to 20 seconds, the decrease in the amount of A is directly related to the increase in the amount of D per se. And really, this rate expression is based on stoichiometry. So really what the rate expression is it's sort of a stoichiometry equation. I actually don't love using it, but I do feel the need to teach it because you might come across it again. So an example type of problem that you might have is something like this. Write the balanced equation that has the following rate expression. So we could be given an expression, an equation, and asked to write the rate expression, or we could be given the rate expression and asked to write the equation. So what we're looking for here is, so let's start, actually I'm going to start with the reactants and the products. So everything that has a negative sign is going to be a reactant. So, because the reactants are decreasing, right? So my reactants are bromine and bromine trioxide ion and, oh, another one, and hydrogen ion. And then now these are positives, so these are going to be my reactants. Not an equal sign, a reaction arrow, bromine, and water. All right, and then this number in the denominator here represents any coefficients. So I have a coefficient of 5 here. There's no coefficient, there's just a 1 in front of bromine trioxide, coefficient of 6 in front of hydrogen, coefficient of 3 in front of bromine, and a coefficient of 3 here in front of water. So this would be the reaction, this would be the rate expression. This is a reaction equation, and this is the rate expression. Seems like it makes sense when I'm saying it, but trust me, you're going to get a problem later. It's going to ask for the rate expression. You'll be like, what's the rate expression? So you need to know these terms, be able to know what it's asking you to actually write. Okay, so if we know the rate of change of one of the reactants or of the products, then we can use that. What this rate expression means, what this stoichiometry is that we can use it to predict the rate of some other part of the reaction, some other substance. So let's look at an example reaction with real chemicals. So we've got hydrogen gas plus iodine gas reacts to form 2 moles of hydrogen iodide. And it says, calculate the average rates of H2 depletion and hydrogen iodide production during the following time periods. So we have this data. So it gives us this data chart. Data, not date. And it wants us to calculate the average rates of, so that we want to know what the rate of hydrogen depletion is. Hydrogens are reactants, so of course it's going to be decreasing, and hydrogen iodide production. And that, of course, is a product, so it's going to be increasing. So first thing we can do is write out the rate expression here. So for 0 to 20 seconds, actually no, I take it back. I'm going to first find the rate for H2 at each of these time points. Okay, so for 0 to 20 seconds, the rate is going to be the change in concentration of H2 over the change in time. That's what I'm going to use for each of these time points. Oops, 40 to 60. I don't want you to think that's a division sign. Okay, so from 0 to 20 seconds. So our change is always final minus initial. So from 0 to 20 seconds would be our final. So our final concentration at 20 seconds is 0.670 molar minus our initial concentration, 0.100 molar. Oh, and this is a reactant, so I can't forget my negative sign in front. Always losing those negative signs. All right, divided by our change in time. And our change in time is going to be 20 minus 0, 20 seconds from, it's going to be total 20 seconds. So I end up with an answer. So 0.67 minus 1 divided by 20 is 0.0165 molarity per second. All right. Now for 20 to 40 seconds, at 40 seconds, I have a concentration of 0.449 molar minus 0.670 molar. All right, divided by, this is another 20 seconds that have gone by. Our change in time is 20 seconds. 40 minus 20 is 20. And our rate at this, for the second 20 seconds, is 0.111 molarity per second. So you can see the rate is going down. It's slowing a little bit. And then in this third time point, the third 20-second interval, our final concentration at 60 seconds is 0.301 molar minus the concentration at 40 seconds. And again, we have a change in time of 20 seconds. And we do the math and we get 0.0074 molarity per second. All right, so that is the rate of the decline or depletion of the H2 at each of those time points. And we can see it's slowing down as the reaction progresses. So, see, rate slows over time. Also note that the rate is always going to be a positive value. So for the reactant, we have this negative sign in front because the change in concentration is going to be negative. So the negative in front negates that, makes it a positive. All right, so now for the rate of the hydrogen iodide production. All right, so according to the stoichiometry of this reaction, okay, we can do this a couple of different ways. So we can use the rate expression. According to the rate expression, all right, the negative change in H2 gas over time is going to be equal to 1/2 the change in HI over change in time. Okay, another way to think about this, if this is the rate of H2, all right, is going to equal 1/2 the rate of HI. Or, in other words, if we multiply both sides by 2, then we could say that the rate of HI is 2 times the rate of H2. Okay, all of this is the same thing we could see just by looking at this equation. All right, if we use 1 mole of H2, we were going to make 2 moles of HI. So we're just basically, to find the rate of HI, we're essentially multiplying the rate of H2 by that coefficient of 2. So I like to think of it, I think it's easier thinking of it stoichiometrically. All right, so the rate of the rate of HI is just going to be 2 times the rate of H2. So if we do it that way, from 0 to 20 seconds, from 20 to 40 seconds, and from 40 to 60 seconds, we get the rate of HI production is 0.0165 molarity per second times 2, 0.011 times 2, and 0.0074 times 2. For rates of hydrogen iodide production as follows. So feel free to get out your calculators and check my math here. But you'll also notice that these rates are decreasing as well. So the rate of reactant depletion decreases over time, just like the rate of product production decreases over time. Let's do just one more quick one here. For this reaction, A plus 2B reacts to form 1/2 C under certain conditions. The rate of A is 0.100 molar per second. What is the rate of B and what is the rate of C? So using the stoichiometry, all right, rate of B is going to be, so for every 1A, we use 2B. So the rate of B is going to be twice that, the rate of A. Or we could also think of this as multiplying it by the mole ratio. So the rate of A, all right, and there's 2 moles of B for every 1 mole of A. All right, so the rate of B is going to be twice the rate of A. So the rate of A in this case is 0.100 times 2 over 1, using the mole ratio there, is equal to 0.200 molarity per second. Ah! Hate it when I do that. Molarity per second. Okay, and the rate of C is going to be 1/2 the rate of A, or in other words, rate of A times 1/2 over 1, because that's the mole ratio here. And so 0.100 times 1/2 equals 0.050 molarity per second, and that would be the rate of C. Okay, so those are just some examples calculating the rate of depletion of reactant and the rate of increase of product. So concentration will affect the rate of the reaction. Generally, if we think about the rate over course of the reaction, as the reactant gets used up, the rate slows down. So if we start with more reactant, the rate will be higher. If we start with less reactant, the rate will be slower initially. And so each reactant in an equation has a certain, might have different effects on the rate. And so the math that we use to identify what the relationship of a concentration of a single reactant is on the rate of the reaction is called the rate law. Okay, so the rate, if we have this generic reaction, A reacts to form B or A forms products, the rate law, and this is different than the rate expression, okay? The rate law is that rate equals some constant times the concentration of our reactant A to some power, okay? K is the rate constant. The concentration of A, that's the concentration of the reactant. Trying to tighten my stylus tip so it doesn't make an obnoxious noise. And then, I didn't want to do X. I wanted to use N as my variable here. Not terribly important, but we'll see why in a minute. Okay, whereas N represents the reaction order. All right, and this is a new word for us. What is the reaction order? So the reaction order is something that we're going to determine experimentally. All right, it's not determined from the stoichiometry. It's determined through experimental data. But what I mean by the reaction order is thus. Okay, so if that N equals 0, then that means that this is a 0 order reaction, which is just a fancy way of saying that the reaction rate does not depend on the concentration of the reactant. It does not matter how much reactant you have, it will happen at the same rate. It doesn't matter. So in other words, if you double the amount of your reactant, then the rate stays the same. So let's see. I think probably a zero order reaction would be, now let me give you an example of a zero order reaction in the real world. I'm just looking it up now. That one's okay. Yeah, I don't have a good one. The Haber process, which we actually use all the time in our example reactions. But I'm trying to think of one where it's a solid. Okay, sorry. Now I'm just going to bore you. Nope, I can't think of one. I'll tell you in live class, I suppose. An example, a good real world example of a zero order reaction, but it's one where it doesn't matter how much reactant you have. It doesn't matter what the concentration of the reactant is. It doesn't change the rate of the reaction. A first order reaction is an N equals 1. And we call that a first order reaction. All right, and in a first order reaction, the rate is directly proportional to the concentration of the reactant. So in other words, if you increase the concentration of the reactant by a factor of 2 or 3 or 4, then you increase the rate of the reaction by 2 or 3 or 4. If A doubles, the rate will also double. If A triples, the concentration of A triples, then the rate of the reaction will triple, and so on and so forth. And if N equals 2, then we have a second order reaction. And in a second order reaction, rate is proportional to the concentration of A squared. So in that case, if A doubles, then the rate quadruples. All right, because if A doubles, so we have 2 times A, 2 squared is 4. If the concentration of A tripled, all right, 3 squared is 9. The rate would be 9 times faster, and so on and so forth. It says an exponential relationship. So we can graph these out. If we have a first order, second order, or zero order reaction, all right, so a zero order reaction, if this is concentration of A on the x-axis, and this is the rate on the y-axis. Okay, so in a zero order reaction, all right, so it does not matter what the concentration is. So as we increase the concentration, the rate stays the same. So this is a zero order reaction. As we increase the concentration, the rate stays the same. For a first order reaction, all right, as we increase the concentration, the rate is going to increase as well in a linear fashion. So as we increase the concentration, this is a first order reaction. We get a straight line. They are directly proportional. Okay, I meant that to be a different color, but whatever. And then for a second order reaction, it's an exponential increase. So as we increase, it's a curved line. It's an exponential curve, and I can't draw that very well. Let me try again. Okay, this is a second order reaction pattern. Okay, so sometimes questions will just show you this graph. Like it'll show you a graph and it'll say, you know, oh, here's a graph, and over time, as we increase the reactants, the rate of the reaction increases as well, and it forms a straight line. Is this a first order, second order, or zero order reaction? This would be a first order reaction because the relationship between the concentration and the rate in a first order reaction is linear. If it was an exponential, if it was a line like this, all right, then we'd say it's a second order reaction. If it was a straight line like this, then we would know it was a zero order reaction. Ooh, that's cool that I did that. Okay, so that's just, you do need to understand this graph. It's just another way for questions to be asked about these different relationships. Okay, so now that we know what the order means, the order tells us how changing the concentration of a reactant will affect the rate of the reaction. But now we need to figure out, well, okay, so then how do we figure out what order how do we know if a reaction is first order, second order, or zero order? And we can only figure that out experimentally. So we have to be given reaction data using different concentrations and measuring the rates at different concentrations of reactant. And then we compare two of those data points so that we can see how the rate is affected when we change the concentration. So essentially what we're going to do is we're going to do a ratio of the rate loss from the different trials. So we'll take, trial 1 and trial 2, and we'll create a ratio, and then we'll use that to solve for x. So we'll take, well, I'll show you in this example. Okay, so I'm just going to switch my color because I feel like it. What's in this example, we have a reaction A reacts to form B, very simple. What is the order of the following reaction, and what is the rate law? Okay. It's not going to ask this normally. It'll just ask you, what is the rate law? In order to find the rate law, you need to figure out the order. So the sort of, the rate law, like sort of sketched out, is going to be this. All right, with an N there. Okay, so we need to figure out what that N is in order to be able to actually write the rate law. Okay, we also technically need to figure out that K, and we're going to do that in the next part of the problem here. But for this part of the question, I was trying to be specific. What is the order? We're trying to figure out what the order is so that we can write the rate law. Okay, so we have 3 different trials that were performed of this reaction, and there were 3 different concentrations of A in each trial, and we measured the rate of the reaction at each of these concentrations. So what we're going to do is we're going to pick 2 data points and compare them. And we are going to divide the rate laws for each of those trials. So let's see, let's pick, and we could pick any 2 in this case. So I'm just for fun gonna pick trial 2 and trial 3. So I like to put the one with the larger rate on top because the math just works out a lot nicer. So the larger rate, the faster rate is trial 3. So I'm going to do trial 3 over trial 2. So the rate law is the rate equals K times the concentration of A over N. So for trial 3, the rate we'll plug in from trial 3 is 0.240 molarity per second equals K, which we don't know, times the concentration of A in this trial was 0.40 molar to the N power. I'm going to divide this by trial 2. The rate in trial 2 is 0.060 molarity per second equals K times 0.20 molar to the N power. Okay, so I can do some division here. So 0.240 divided by 0.06 is 4. I'll say 4.0. All right, the K's cancel out because K divided by K is 1. And then 0.40 divided by 0.40 to the N power divided by 0.2 to the N power is going to be 2. 0.4 divided by 0.2 is 2. 2 to the N power. Okay, so what to the N power, or 2 to the what power equals 4? In this case, N equals 2. 2 squared equals 4. All right, so the rate law for this reaction is rate equals K times the concentration of A squared. All right, we solved for that order. In other words, this is a second order reaction because the N equals 2. We can also solve for K because once we know the reaction order, we can just use that experimental data from any one of these 3 trials, plug it into this equation here, and solve for K. So let's do that. Let's do it, and we can pick any single one of those. So we use this rate expression down here. Sorry, not rate expression, this rate law. Rate law and rate expression are different things. Okay, so I'm going to pick trial, what trial did I pick here? Trial 2, just because. So the rate for trial 2 was 0.060 equals K times the concentration for that trial was 0.20 molar, and we square that because N equals 2. And I should keep my units here, so that's molarity per second. All right, I'm going to divide both sides by 0.20 molar squared. All right, so that I can solve for K. And I end up with K, funky looking K there, is 0.60 molarity per second divided by 0.040 molarity squared. So my K is going to be 1.5, and one of those molarities cancels out, but I end up with 1.5 inverse molarity and inverse seconds. So both of those units are in the denominator. Okay, so the value or the units of K are going to vary based on the reaction order because you're going to have different units depending on what that exponent is. So for a second order reaction, which this is, the units are inverse molarity times inverse seconds, or 1 over molarity per second. But for a zero order reaction, it will be molarity per second. And for a first order reaction, it's just going to be seconds. There will be no molarity in the units for K. So sometimes a question might ask you, the rate constant for this reaction is 45 inverse seconds. Is the reaction first order, second order, or zero order? And you can deduce it by doing a little bit of math or just by referencing this table. Okay, so let's do another example where we find the reaction order and the K value. Okay, so we've got this reaction, A goes to B, we're still using the simple reaction, has been experimentally determined to be second order. So it's telling us in this reaction that it's second order. We don't have to solve for the order. So we could go ahead and write out the rate law for this reaction. The rate law is equal to K times the concentration of the reactants to their powers. Okay, so this one is, and the only reactant here is A. Notice that the product has no place in the rate law. That's another thing to note. It's only the reactants that have a place, because it's the reactants, the concentration of the reactants that determines the rate of the reaction. All right, at the start of the reaction, we only have reactants. We don't have products. So their amount is irrelevant. So what we're starting with, that is relevant. That's why only reactants go into the rate law equation. Okay, so this would be the rate law for this reaction because it tells us that it's second order. Now it says the initial rate is 0.0100 molarity per second at an initial concentration of 0.100 molar. So I'm just going to write that down. At this concentration of A, 0.100 molar, the rate is 0.0100 molarity per second. Then it says, what is the initial rate at this higher concentration, where we have a concentration of 0.500 molar. So we want to know what is the rate at this time. Okay, so we can figure out the rate using this equation here, this formula, which is known as the rate law. So in order to figure out the rate at 0.5, we can't just plug in this second value here because we don't know what K is. So we have two variables and we need to figure out what K is first in order to be able to plug other numbers in here. So the first thing we're going to do in this problem is solve for K. And so we're going to just plug in these numbers, the initial numbers that were given, into the rate law so that we can solve for K. So the rate that we were given was 0.0100 molarity per second equals K times the concentration of 0.100 molar squared. And we solve for K. I'm not going to do all the rearrangements. I'm just going to tell you K equals 1.00 inverse molarity times inverse seconds. Okay, so now the second thing we can do, now we can use the rate law and our newly solved K value. And we can figure out what the rate is going to be when the concentration is 0.5. So our K, 1.00 inverse molarity per inverse second times our new concentration of 0.500 molar squared. And when we do that math, we end up with a rate of 0.25 molarity per second. One of these moles cancels out with that, molar, and we get units of molarity per second. Rate is always going to be molarity per second. It's only the units of K, the rate constant, that change depending on the order of the reaction. All right, so far we've done reaction order with reactions that only have a single reactant. But some reactions, as we know, have multiple reactants. So if we were to write out one of these equations, so let's say some generic reaction where we have A plus B reacts to form C plus D. Okay, the rate law for this reaction is going to be that the rate of the reaction is dependent, it's the rate constant times the concentration of reactant A to its power, whatever order it is, times the concentration of reactant B to its power. So X X is the order of reaction with respect to A. In other words, what effect the concentration A has on the rate of the reaction. Y is the order of reaction with respect to B, to reactant B. Okay? And so we could say that the reaction is first order with respect to A and first order with respect to B, or second order with respect to B. And the overall reaction order is going to be X plus Y. And so if we had a reaction that was, if the rate law was, just to give you some examples, right? If the rate law was this, oops, nope, still on erase here. All right, so if the rate law was this, all right, if the reaction was second order with respect to A and B, then it would overall be a fourth order reaction, which exists. We just are not going to get into those, but that's what that would be. If the reaction were this, oops, all right, it would be first order with respect to A. All right, if we have an exponent of 1, we don't usually write it. So if there's no exponent, then that's an exponent of 1. All right, it'd be first order with respect to A and second order with respect to B. And it would have an overall it would be a third order reaction. Okay, so that's just some examples of some simple concept check questions that, you know, you could be given a rate law and then asked, what's the overall reaction order? So let me go back to my original X and Y here. All right, so if we are given a reaction with 2 reactants and we need to solve for the rate law, we need to determine the rate law of the reaction, we need to not just find N, like we were finding before, we need to find both X and Y. We have 2 exponents we need to solve for. And so we're still going to use reaction data. We're still going to compare the ratio of one trial to another. But we're going to specifically, if we want to solve for X, then we want to find 2 trials where our concentration of A is changing, but the concentration of B is not, so that we can sort of cancel those out, as you'll see. And if we're trying to find the exponent Y, which is the exponent for B, then we want to find trials where the concentration of B is different, but the concentration of A stays the same. Sort of we're controlling there. All right, and then after we determine the rate law, we determine the value of X and Y, those exponents, we know the order of the reaction, then we can determine the rate constant of the reaction by just picking one of the trials to plug into our rate law. So let's do an example problem. Here we go. Determine the rate law and the value of K for the following reaction based on the experimental data provided. So here we have an actual reaction, not A's and B's, but a chemical reaction. We've got nitrogen dioxide plus carbon monoxide react to form nitrogen monoxide and carbon dioxide. All right, and we've done 4 different trials where we have altered the concentrations of each reactant, the nitrogen dioxide and the carbon monoxide, and we measured the initial rates of these reactions. So the first thing we need to do is figure out the rate law. And the rate law is the name of this equation, right? So the rate law for this is going to be the rate constant times the concentration of the first reactant to some x power times the concentration of the second reactant to some y power. So in order to solve for x, I'm going to solve x first. And I need to pick 2 trials where the concentration of NO2 differs, but the concentration of CO stays the same. So I'm going to pick trial 1 and 2. Trials 1 and 2, because in these 2 trials, the concentration of carbon monoxide stays the same, but the concentration of nitrogen dioxide is different. And I like to put the one with the faster rate on top, so I'm going to compare like this, rate of trial 2 over I'm just going to do it like this. I'm going to do the ratio of the rate laws for trial 2 over trial 1. So trial 2 has a rate of 0.0082 molarity per second times K times the concentration of NO2 in trial 2 is 0.20 molar to the x power times the concentration of CO in trial 2 to the y power. Now we're going to divide this by the rate law for trial 1. So trial 1 has an initial rate of 0.0021 molarity per second equals K times the concentration of nitrogen dioxide is 0.10 molar and of carbon monoxide also 0.10 molar to the y power. Okay, so now we can solve for K, we can cancel out K because they are the same. K divided by K is 1. And we can cancel out 0.1 molar to the y power because those variables are the same as well. And so now we are down to a single variable, x. And x is what we're solving for. So 0.0082 divided by 0.0021 comes out to be 3.9. And 0.2 divided by 0.2 to the x power divided by 0.1 to the x power is 2 to the x power. Okay, so 2 to what power equals 3.9? And 3.9 is pretty close to 4. We're going to round that to 4. And so we're going to say that x equals 2. 2 squared equals 4. So in this case, we've solved x here. I'm just going to replace that with our 2. Okay, now let's solve for y. We need to use trials now to solve for y where the carbon monoxide is different, but the nitrogen dioxide is the same. So I'm going to use trials 2 and 3. And again, I like to put the trial with the faster rate or the higher rate on top. So in this case, well, they're about the same, but the third one is a little bit higher. So trial 3 over trial 2. So I'll do it that way. Okay, so the rate of this trial 3 is 0.0083 times the rate constant, the concentration of nitrogen dioxide, which is 0.2, goodness gracious, 0.20 molar to the x power, or we could plug in 2, because since we already found it, but it's not going to matter much because it's going to cancel out anyway. And then to the y, this one, trial 3 is 0.20 molar to the y power. Now for trial 2, now whether we have an x here or a 2, it doesn't matter because these are going to cancel out because they're identical terms, just like k is going to cancel out. And let me just finish filling this out. This is the concentration of carbon monoxide in trial 2, which is here, to the y power. Okay, so 0.0083 divided by 0.0082. So I said these cancel out, and this equals 1. 1 equals, and then 0.2 divided by 0.1 is 2 to the y power. So what 2 to the what power equals 1? You might need to refresh your memory on exponent stuff, but anything to the 0 power equals 1. So 2 to the 0 power, in this case y, equals 0. So the rate law for this reaction is that the rate equals K times the concentration of NO2 squared times the concentration of CO to the 0 power. Or the other way of writing that, since anything to the 0 power is 1, in other words, the rate law for this reaction is really only dependent on one reactant, on the NO2. So another way to write this, and actually the more correct way to write this, is just leaving that carbon monoxide out of the rate law equation. All right, and then the second part, it did also ask us what is the value of K. So we can figure that out now. I'm going to say this is sort of like the second part of the problem. And we can do that using any one of those trials and plugging that data into the rate law equation. So I'm going to use trial 4 and plug it into that data into this equation for the rate law. So the rate of trial 4 is 0.033 molarity per second equals K times the concentration of NO2, and that trial was 0.40 molar squared. We don't care about the concentration of carbon monoxide because it's 0 order with respect to carbon monoxide. The concentration of carbon monoxide does not matter. Okay, so now we solve for K, and K equals 0.033 molarity per second divided by 0.4 molar square, which is 0.16 molarity squared. So one of these cancels out with that, and we get a value of 0.21 inverse molarity and inverse seconds. And that is the value of our K. All right, with the units of inverse molarity, inverse seconds. So now we could presumably, potentially, be asked a third part of this question. It could say, based on the rate law, what do you expect? What would you expect the rate of the reaction to be at such and such concentration of nitrogen dioxide if we had a concentration of 0.55 molar nitrogen? So at any concentration of nitrogen dioxide, we should be able to predict the rate using this equation. All right, we determined the rate law from experimental data. A few data points help us to figure out this rate law, and now we can use the rate law to calculate or estimate what the rate would be at any concentration of NO2. All right, so an important thing to note here is that the reaction order is not related to reaction coefficients. So if we look at the equation here, all right, none of these all have a coefficient of 1, right? Everything in this reaction has a coefficient of 1. Okay, so the NO2 has a coefficient of 1, and the carbon monoxide has a coefficient of 1, all right? But the NO2 had a reaction order of 2, and the CO had a reaction order of 0, okay? So the coefficient is not the same thing as the reaction order. The reaction order must be solved using experimental data. Okay, so when we're talking about rate expressions, that first part, we're talking about the rate of depletion of thing A versus the rate of appearance of product B. Okay, that's different. That is related to stoichiometry. But the rate law, when we're trying to determine the effect of concentration on the rate of the reaction and in terms of reaction order, it is not related to the coefficients, okay? All right, so let's do one more that I'm gonna have you guys try this one. This would be a good time to pause the video, try it yourself, and then come back here for the work. Okay, so try this one. Here's the equation right here. Here's the trial data. So we get a table of trial data, and we want to determine the rate law for the reaction, and we want to determine the rate constant for the reaction. So for the first part, the rate law, the sort of rough rate law, the sketch rate law for this reaction would be the concentration of CHCl3 to the X power times Cl2 to the Y power. Those are our two reactants. Remember, we don't really care about the products when we're determining rate law. We're just looking at the reactants. So in order to determine X and Y, I want to use a ratio of two of these trials. So to determine X, I'm going to use trial where I want the CHCl3 concentration to be different. So I don't want to use trials 2 and 3. But I do want the concentrations of chlorine to be the same. So I do want to use, the only trials I could use actually are trials 1 and 2. Because those are the only two trials where the concentration of the chlorine gas is not changing. It's the same. So I always like to do the faster rate on top and the slower rate on bottom because it just makes the math easier. Oops. Trial 2 over trial 1 is how I'm going to set this up. Okay, so the rate of trial 2 is 0.06, two zeros, 69 molarity per second equals K times the concentration of the CHCl3. So in trial 2, that was 0.20 molar to the X power times the concentration of the Cl2 in trial 2 is 0.10. I'm going to divide all of this by the rate law for trial 1. And trial 1 had a rate of 0.0035. And the concentration of the CHCl3, oops, I forgot a 0 here. I wrote these numbers wrong. I can't even read what I've written. 0.020. There we go. Okay, so now what's going to happen is K divided by K is going to cancel out, and 0.01 to the y power divided by 0.01 to the y power is going to cancel out, and now I can solve for x. So 0.0069 divided by 0.0035 equals 1.97, which is pretty darn close to 2. And 0.02 divided by 0.01 is 2 to the x power. And so 2 to what power equals 2? Our x variable equals 1. 2 to the 1 power equals 2. All right, so this is going to be first order with respect to CHCl3. So now we need to figure out y. What is y? And for y, we need to use two trials where the CHCl3 stays the same. So in this case, I'm going to use trials 2 and 3. Trials 2 and 3. And I'm going to do trial 3 over trial 2 because I like the faster rate to be on top because it gives me a whole number, or it gives me a number above 1. And I just find that easier to work with because I can solve for x in my head that way. Okay, so trial 3 has a rate of 0.0288 molarity per second, and times K times the concentration of CHCl3, which is 0.020 molar to the x power or to the 1 power, either way. And we also had a 0.20 molar concentration of the chlorine in that trial. Now we're going to divide it by the rate law for trial 2. Trial 2, 0.0069 molarity per second. K, still 0.020 molarity for the CHCl3. And for the chlorine gas in this trial had a lower concentration. So again, our K's are going to cancel out. So are these first variables. It's identical, so they're going to cancel out. 0.0288 divided by 0.0069 equals 4.06, which is pretty darn close to 4. And 0.02 divided by 0.01 equals 2 to the y power. So 2 to what power equals 4? 2 squared equals 4. Y equals 2. All right, so we can replace our y with a 2. So the rate law for this reaction is that the rate equals K times the concentration of CHCl3 to the first power. I don't need to write anything there. I just leave it blank. An exponent of 1 does not need to be written. And chlorine gas to the second power. So this would be the rate law. What would the overall order of this reaction be? Hopefully you answered third order reaction. All right, overall this would be a third order reaction. We would say it's first order with respect to CHCl3 and it's second order with respect to chlorine, the Cl2, but it's third order overall. So to complete this, the second question here, it said determine the rate constant K for the reaction. So I'm going to do that in green, little color coding here. So the rate constant, we need this rate law in order to figure out the rate constant. So we're using this rate law. And we're going to pick, we're just going to use data from any one of these trials. And any one of them should give us the same answer for K, because K is a constant. So no matter which trial we use, no matter what the concentration and rate data we use, we should always get the same value. That's the definition of a constant. So pick one, any one, your favorite one. I like 4. 4 is my favorite number. My birthday's on the 4th day of October. So I'm going to go with trial 4. Okay? And that's, totally arbitrarily my choice. So the rate of that trial is 0.224 molarity per second equals K. The concentration of each in that trial was 0.04 molar. So I'm going to plug in those concentrations here, square that one. All right, and now I just solve for K. So I'm going to divide both sides. Essentially, what I have is 0.04 to the third power, because I have 0.04 times 0.04 squared. So 0.04 to the third power, molarity. All right, so that's going to cancel those out. So now I've got K isolated. So 0.224 molarity per second divided by 0.04 to the third power gives me a K of 3.5, and then the units are inverse molarity, like squared, seconds squared. Right, because it is a third order reaction, so it is going to have different units than what we have seen in previous problems. So we solved for K. So a third part of the question that could be asked, I'm going to give myself a fun new color. Okay, so we're done with the problem. It asked for the rate law, and we found the rate law. And it asked for the value of K, and we found the value of K. So the third, it could potentially have a third part of the question that asks, what is the expected initial rate when the concentration of CHCl3 is 0.33 molar, and the concentration of Cl2 is 0.11 molar. And I just totally picked those numbers off the top of my head. Okay, so we could figure that out using the rate law. The rate would be expected to be K, 3.5. Oh, and sorry, that's 3.5 times 10 to the third. It wasn't 3.5. 3.5 times 10 to the third. I distracted myself. So 3.5 times 10 to the third, inverse molarity per inverse second there, times the concentration of the CHCl3 to the 1 power times the concentration of the Cl2 squared. We're just using this rate law here, plugging in these values into the rate law. and we get a rate of, I don't know, I need my calculator because I just made this up off the top of my head. And do times 0.33 times 0.11 times 0.11. And we would expect it to be a rate of 13.97, which is basically going to round to 14.0 molarity per second, which is quite a bit higher than the rates up here because our concentration was quite a bit higher. Okay, so lots of different ways we could be asked questions. The key is understanding how to get the rate law for the reaction and how to get the rate constant, solve the rate constant for the reaction. So practice that, and we'll come back for the second part of kinetics next time.